morning. This is Quantum Communications for Securing the Smart Grid. This is a collaboration between Los Alamos National Laboratory and the University of Illinois. And our team is myself, Beth Norville from Los Alamos.
And I'm Raymond Newell from Los Alamos.
Glenn Peterson from Los Alamos.
Tim Yardley, University of Illinois.
Jeremy Jones, University of Illinois.
And we would like to thank our sponsors, Dr. Diane Hui and Dr. Carol Hawk, for supporting this program. And we would particularly like to thank the TCIPG consortium for hosting us here in their test bed. They've been extremely nice to us and helpful in recording us and setting up web exit for us, et cetera, et cetera. I can't say enough how thankful we are for all the hospitality and helpfulness. Thank you both. So this is our test configuration. We have a real-time digital simulator sending data to phaser measurement unit. The phaser measurement unit has an Ethernet connection into one of the quantum communication systems. That is then communicated over 25 kilometers of optical fiber, decrypted by another quantum communications computer, and that is fed back into a phaser data collection software running on this computer here.
So as Beth said, we have a power simulation that's running, feeding data into this. And what we've done is we've set up a high fidelity power simulation running what's called the WSCC 9-bus model. That's running on the RTDS that's here in the TCIPG lab. That's running at a 50 microsecond level power simulation, giving us the real fidelity of deploying this QKD simulation in the field, being able to verify that in the lab here without actually having to deploy it in the field. So in that simulation, we actually are feeding all of that data through our deter cluster here, which is part of our automation and capabilities that we've set up in the lab to provide experimentation and infrastructure for supporting these types of projects. So we've actually utilized that framework here for this experiment as well, showing the flexibility of that. And that's providing us with the instrumentation to pipe the data from the RTDS to the quantum cryptography cluster here that they have set up, and they'll be showing you in a bit. And the 9-bus model that's running, which is shown in the slides here, is what's actually running on the RTDS. And in the model that we're running, this high fidelity simulation, we're actually simulating a fault. So in this fault, what we're showing is not only does the quantum cryptography system able to handle the normal data coming through, but that it responds similarly in the cases of seeing abnormal data as well. In other words, that it's unaffected by the behaviors that it would see in the real world, in addition to the perfect environments that it sees in say, a perfect simulation. So the 9-bus model is representative of a reduced model of the Western connection system. And it's a model that's often used for simulations to prove out and validate theory. This is also a model you're familiar with from other TCIPG demonstrations, and one we've used in many cases. So in this case, we're causing a short circuit fault on the 9th bus, and this data is sent through a Schweitzer relay. And that Schweitzer relay is communicating that information through to the quantum system, which is then encrypting it and sending it to the other side, which is decrypting it, and then sending it to the PDC simulator, which is also running on the TCIPG testbed. And they'll talk more about the quantum system in a bit as to what it's doing. But once that information is decrypted, it's then visualized on the PDC and shown just as if it were being shown in a normal system. So it goes from a real high fidelity power simulation, which is traditional power equipment, through the quantum systems, and then shown again on a traditionally deployed phaser data concentrator, just as if it were in a normal power system as well. And in between there is the magic that they'll talk about next.
Thank you, Tim, and thank you, Beth. I'll say a few words about the quantum cryptography system, which is at the core of this demonstration. This system, think of it as an encrypted pipeline for the data. We take data from the PMU, from the relay, encrypt it for transmission, and then decrypt it at the other end and return it decrypted and unharmed to the rest of the TCIPG testbed. So I'll go through the steps that make that happen in a bit more detail. In this orange crate, we have our single photon transmitter, what a cryptographer would, in our cryptography system, we would call ALICE. This box contains a laser and a polarization state generator that makes single photons, one at a time, in one of 4 possible polarization states. Those come out on this fiber, go through some attenuators, and in this deck get mixed with the much brighter classical communication signals, which are at 1310 nanometers. Our single photons are at 1550 nanometers. Both wavelengths get mixed here and sent over one single fiber through a 25-kilometer fibrous spool, just barely visible inside this black case. You'll see that fiber come out in the orange cable between these two and come over here to our QKD receiver, which is in this big blue box. That receiver separates out the classical communication, which has the majority of the data payload on it, from the single photons, which are what are used to instantiate the quantum key distribution channel. The 4 single photons get analyzed according to their appropriate polarization states and detected by a set of 4 single photon avalanche photodiodes present inside this refrigerator. Those signals come up to these timing electronics and are analyzed by this set of computers to be able to extract the single photon timing information and execute the quantum key distribution protocol. The output of the quantum key distribution protocol are cryptographic keys, which show up over here in this computer, which this is Bob, and also in ALICE. Recall that the QKD protocol generates shared secret keys at both ends of the 25-kilometer of fiber in such a way that no eavesdropper who has access to those 25 kilometers of fiber would be able to extract or learn any information whatsoever about bits in that key. Once those keys are generated inside the system, Alice and Bob both maintain a register, kind of a buffer, of key material. In this case, we've coded up a buffer of 256 bits, 256 key slots. As those slots are filled by keys generated by the QKD system, one of these little green lights turns on, indicating the presence of a good, valid, truly quantum secure key. And so as you can see here, this has been running now for about 20 minutes behind me for the rest of the talks that we've heard this morning. We've generated, well, about 200 keys have been generated in that time. Concurrently with that, this system is communicating with the rest of the TCIPG testbed over a standard Ethernet port, TCP/IP connection. Ports exist between our Bob computer and the PMU relay device that Tim indicated earlier, and between our ALICE computer and this phaser data concentrator system that Tim explained earlier. And as our Bob machine receives data from the PMU, that data is encrypted in real time with these secret keys as they get read out of the buffer and sent over the 25 kilometers of fiber, the exact same fiber, recall. We're making the secret keys and sending the data over a single strand of single core fiber over to this computer and then sent. So here on screen you'll be able to see some things that indicate that this is taking place. On this computer we have 2 running versions of PMU Connection Tester. This is a program that reads data from the PMU and displays it on screen. You'll see this window, we have PMU data from the TCIPG testbed coming through and it looks good. This is looking at the unencrypted stream prior to encryption and transmission. This window is looking at that exact same data, those very same C37 data frames after having been encrypted. And so this is the sort of information to which an eavesdropper would have access. Perhaps you'll be able to see here that when I click the connect button, as an eavesdropper might wish to do, what shows up is an awful lot of exception, bad data stream, expected sync byte not present. An error has appeared here on screen as this piece of software is attempting to parse and extract useful data from what we have encrypted. And so this is a demonstration that no eavesdropper would be able to get access to that data as it is being sent. As you can see here behind me, more green lights are being filled in as keys are being generated. We also have here on screen a demonstration, or in fact a real-time measurement of the overall latency of the encryption system. This is a measurement of the amount of time that takes place from receipt of a valid C37 data frame by this computer to when that very same, to its encryption, its transmission along the fiber, its decryption, and its generation here when that data frame becomes available to the phaser data concentrator on this computer. This is a measurement of all the time that's required for all those steps to take place, currently showing up 260 microseconds. So that's a quarter of a millisecond. A few things I might like to say about that. One is that of that 260 microseconds, about 100 of those microseconds is the time of flight of the speed of light through that fiber. Right, so not quite half of the overall latency is due to the speed of light being too slow. The other 160 microseconds is the algorithmic processing time of the encryption and the decryption steps. So we're fairly proud of that number. We hope you'll find it satisfactory. As we can see over here on this side, the same data is being received by after transmission through the fiber. Again, we have an instance of PMU connection tester attempting to decrypt that data, or attempting to analyze the data prior to decryption, and as we saw on this side, it fails because that data is still encrypted, and to show that data is now completely inaccessible to any eavesdropper or adversary. However, after the decryption takes place, we have the data come out here as one would like. An important feature of the C37.118 communication protocol, which transmits data back and forth between phaser measurement units and phaser data concentrators, is that it is indeed back and forth. That this is a bidirectional communications protocol. As commands are sent from PDCs to PMUs and data is returned from PMUs to PDCs, we require bidirectional comm between the two. We have in this system encrypted both directions of that communication with dedicated keys drawn from the pool of key material generated at both ends. And to demonstrate that here, we see that right now data is flowing from the PMU to the PDCs, as we can see here on screen. A green arrow there indicates the direction of data flowing that way, which is sort of heuristic for from PMU to BDC. If we ask Glenn over here to request to send a command from the PDC to the PMU to suspend the flow of data, you may have seen here behind me this green arrow indicating data flow in the opposite direction light up. But in any case, you'll certainly have noticed that the data flow has stopped as Glenn has requested a suspension of all data. Glenn in just a moment will request the data be returned, and we'll see that the request command, which is flowing from the PDC to the PMU, is about to light up, and as it does so, the PMU will respond by beginning to return data. There went the request, and here comes the data on its way back. Bidirectional comm, encrypted with quantum keys, independent and separately chosen quantum keys in both directions.
Oh, thanks, Ray. Well, I'd like to say a few words about this system. It was built from previous systems that we had. We did this to be cost effective. We're using laboratory equipment. It may look rather large, but the fact of the matter is that it's been built with laboratory equipment, and we have a lot of experience in miniaturizing hardware, and this system could be made into something much smaller and lower power still. For example, what you see in this box here, one of the major components here is this transmission unit that Ray discussed. It's about the size of my finger. So you're seeing a pretty big box here. There are some other components in here, but that can be significantly miniaturized. And again, over here, we have this large refrigerator down here to cool our single photon detectors. Well, what's in that refrigerator is again about the size of my finger. So again, that could be miniaturized significantly. But to show you what we wanted to do was to show you the basic technique, what we can do with low latency for the smart grid, and not necessarily, and to do it as cost effectively as possible. We didn't miniaturize everything. So I just wanted to point that out. It's a great system, but we didn't put a lot of engineering into miniaturization.
Concludes our demonstration of the quantum key encrypted PMU PDC communication here, our collaboration between the Los Alamos National Laboratory and the TCIPG testbed at the University of Illinois Urbana-Champaign. Thank you.